Yeah, ladies and gentlemen, you are welcome. So in this video, we are going to look at the concept of heat capacity. Don't forget to subscribe, follow, and join to my YouTube community for more videos. Introduction to heat capacity. So when we said heat capacity actually is the amount of heat required to rise the temperature of a substance by 1 degree Celsius or Kelvin. Let's say you have a substance here, and the substance, let's say you have a substance here which has a temperature of 25°C. So when this substance is actually absorb heat or is exposed to heat, so the amount of heat that is required to raise the temperature of this object by 1°C is what we call heat capacity. Let's say now the temperature is changed from 25°C to 26°C. So the amount of heat that is required to raise or to increase the temperature of a substance by 1°C or 1 Kelvin is what we call heat capacity. And as you can see from here, the temperature of this object is changed from 25°C to 26°C, and that is what we call heat capacity. So the amount of heat that you require to change the temperature of an object by 1°C is what you call heat capacity. And then very importantly, ladies and gentlemen, this heat capacity is a physical property that varies depending on a material and its mass. So one thing that you need to understand when we are talking about heat capacity is one of the very important physical properties that varies across material. So it depends on the types of the material and the mass of the material. So very importantly, understanding heat capacity, it helps in analyzing how different materials respond to heat. So if you are able to understand the concept of heat capacity, ladies and gentlemen, you will be able to understand or you will be able to analyze how different substances are respond to heat energy. So as we can see, when we said heat energy, so the formula for calculating heat energy, as we can see from here, ladies and gentlemen, you see that the heat capacity, which is the heat total, as you can see, is Q all over delta T. So the C here stand for, the small letter C here stand for, or the capital letter C here stand for heat capacity. And then very importantly, we have also specific heat capacity. So the specific heat capacity, it actually defined as CS. So CS is a specific heat capacity. Of course, the heat capacity is divided into two. We have specific heat capacity and molar heat capacity. So specific heat capacity and molar heat capacity are two different types of heat capacity. And as you can see, that heat capacity is an extensive quantity, while intensive quantity and intensive quantities are specific heat capacity and molar heat capacity. So the specific heat capacity and molar heat capacity are the example of intensive property or intensive quantities. So as you can see, specific heat capacity, the formula for calculating specific heat capacity is Q all over M delta theta. So the M here is mass, then the delta theta is means change in temperature. So, and then we have molar heat capacity. So as you can see that the molar heat capacity Cm is Q all over N delta T. N stand for mole. N stand for mole. So then, of course, as I explained, we have different types of heat capacity. We have, as you can see, we have specific heat capacity, and then we have molar heat capacity. So these are the two types of heat capacity. And as we can see, when we say specific heat capacity, it refers to the heat needed to raise 1 gram of a substance by 1°C. So I think, as you can see from here, in the case of specific heat capacity, we are talking about the 1 gram of a substance. So let's say we have a substance here, and then of course, this one substance has a mass of 1 gram. So when the temperature of this substance, let's say initially it has a temperature of, let's say 20°C. So that when the temperature of 1 gram of a substance is changed from 20 to 21°C, so this is what we call specific capacity. It means it is actually amount of heat that is required to rise the temperature of 1 gram of a substance by 1 Kelvin. So as you can see, or by 1 degree Celsius. So this is a typical example. You have 1 gram of a substance. Initially, the heat or the amount of temperature in that substance is 20 degrees centigrade. And when heat is absorbed, or when the substance is heated, then the temperature change from 21 to 20 from 20 to 21 degrees centigrade. And then the next thing actually is molar heat capacity. So what is molar heat capacity? So as we can see, the molar heat capacity is actually, as you can see, the heat required to increase 1 mole of a substance temperature by 1 degree centigrade. So you see here, the only differences between specific heat capacity and molar heat capacity is that in the case of molar heat capacity, we are talking about 1 mole of a substance. And in the case of specific capacity, we are talking about 1 gram of a substance. So you see the only difference is mass and mole. In the case of molar heat, we are talking about 1 mole of a substance. And in the case of specific heat capacity, we are talking about 1 gram of a substance. So as we can see, ladies and gentlemen, this is the heat capacity and its measures, and it has a formula of Q all over delta theta. And then we have specific capacity, which is one of the types of the of heat capacity. And of course, the formula is Q is equal to MC delta theta. So this S, that is OCS, is specific capacity, and then CM is molar heat capacity. So as you can see, Q is equal to, of course, in the case of molar heat capacity, here is not M, it's supposed to be N. So this is N. So you see, we have molar heat capacity. Here we have Q all over N delta theta. So let's look at some of the examples. So if we have 100 joules of a heat are needed to a substance that its temperature increases by 5 degrees Celsius, the heat capacity is, so remember, ladies and gentlemen, the heat capacity, that is heat capacity C, is equal to, as you can see from the previous formula, is Q all over delta T. So we have Q all over delta T. So the Q here is the amount of heat, which is, we have 100. So we have 100 joule, and then of course divided by the change in temperature. So the temperature here, the change in temperature delta T here is 5 degrees Celsius. So what will happen? So if we now take this 100 divided by 5, is going to give us 20 joule per Kelvin. So this is actually the answer to this question. And then question 2, example 2, determine the heat capacity of a copper of mass 70 gram and the temperature difference is 20 degrees centigrade if 100 joule of heat is lost. So remember, we have the formula that says Q is equal to MC delta theta or delta T. So what are we trying to get from here? We want to determine the heat capacity. So we are going to determine CO specific heat capacity. So therefore, we have to divide both sides by M delta theta. So this one M delta theta. So therefore, this one will now take care of this. Then we now have C is equal to Q all over M delta theta. And as you can see, the Q here is 300. And then the M, which is the mass, is given mass here is 70 gram. And then we have the change in temperature, that is delta theta, is equal to 20 degrees centigrade. So therefore, the M here is 70 times the change in temperature, 20. So when we now take 300 and we divide it by, so at the end, we are now going to have 300. Because now we have 20 times 70, that will give us, of course, we have 300 divided by 1,400. And as you can see, this one will now take care of this. So we now have 3 divided by 14. So therefore, at the end, we are now going to have 0.214 joule per Kelvin per kg. So this is actually the answer, and as you can see, this is what we have. I already solved it, but let me show you from what I have here. Let's see. So we have the Q as 300. So the formula, we have MC delta theta. So we have 300 divided by 20 times 70. And that is how we arrive. Of course, this is the final formula. So this is the final answer, 0.124 joule. Of course, here we have joule. We have joule, of course, as you can see. This is joule per Kelvin per kilogram. So now example 3. Determine the heat capacity of 3,000 joule of heat is used to heat the iron hot mass 10 kilogram from 20 degrees centigrade to 40 degrees centigrade. So see here, of course, ladies and gentlemen, as you can see, we have been given, first we have mass. So the mass here is 10. This is 10. So we have 10 kg. So we have T1 initial temperature of 20 degrees centigrade. And then we have the final temperature, which is 40 degrees centigrade. And then we have the heat, which is Q. The Q is 3,000 joule. So we have this. So what do we do now? So we now take the formula Q is equal to MC delta theta. So the Q here is already given as 3,000. And then the mass, of course, is 10 kg. Then times C, which is unknown. And then times the change in temperature, which is 40 minus 20. So this will now give us, of course, at the end, we are going to make this C subject of the formula. So at the end, C now is going to be 3,000 divided by 10 times, of course, 40 minus 20 is going to give us 20. So therefore, we now have C is equal to 3,000 divided by 200. So this now will cancel this, and then we have 30 divided by 2, which is 15 kilogram joule per degree centigrade. Sorry, let me write it here, 15 joule per kg per degree centigrade. So this is the answer. So ladies and gentlemen, please don't forget to subscribe, follow, and join my YouTube community for more videos. See you in the next example.